let me start from the beginning to create a new projects. For creating the new project, what I will have to do, I will just go to this file options. You can see on the screen there is a file option is there. In the file option, there is called option called new. I will click on the new button. Once I click on the new, I'm starting from scratch. So from the beginning, let's get started how to model the solar cell from the beginning. I click on this file and by default, there is a surrounding with 0 nanometer thickness, unnamed with 100 nanometer thickness, substrate with 100 nanometer thickness. This is a default layer stack is generated. We will modify according to our layer structures. We can design our layer stacks. Now default is this particular stack. I want to create my own layer stack and would like to perform the optical solar cell simulation first. Firstly optical solar cell, and then will convert into the electrical, and optoelectrical calculation will be performed. So I started it, and now I have to add more number of layers. 3 layer is not enough for me. Whatever the number of layer is showing here, surrounding, unnamed and substrate, the layer structure in the right side is automatically visualizing. You can see here surrounding, incoherent, unnamed 100 nanometer and substrate. Right side will automatically happen. Whatever you will do in the left side, the reflection will come occur in the right side automatically. So these are 3 layers that is automatically generated. I would like to add more number of layers. So what I will do, I will click on this add layer. I click on this plus sign and added this unnamed second layer. Naming is not specified. We will specify the name shortly. So by accordingly, the right side pink layer is generated. Similarly, I will click on again add layer and new layer is generated in this sky blue color something. And then I can click on the layer, something new violet layer is generated. So I can click n number of times and my number of layer will generate, and right side it will reflect. Only single click is required to generate that number of layers. Initially so many number of layer is not required. So I would like to delete few of the layers. So I will click on this minus sign to delete the layers. So this layer is deleted. It is a deleted layers. Only few layers are remaining. So I want to define the layer name. The first layer that I want to define is called air, on air, which is incoherent. And there is no meaning of basically thickness. That's why it is mentioned 0 thickness. Second one is called layer, that is called I want to define as a glass substrate, which is 100 nanometer thickness. As an example, I want to take. Now third unnamed layer is there. I want to add it and rename it. I want to define its name, that is called ITU as an example, and would like to change the thickness of this layer. Let's suppose as an example 125 nanometer. If I want to use the millimeter, micrometer, nanometer or wavelength dependent, whatever, I can take that particular units. So this is ITO with 125 nanometer, and this is called P dot. So I will click on this P dot and would like to define the layer thickness. I want to modify, I want to adjust as per my requirement as an example, and whatever your particular requirement, you can use your particular material thickness. Similarly, this is my next layer that I want to rename, and example P3HT. Initially I am taking this material, later on I will take different other material as well and try to simulate the new structures. This is first project that I am trying to create here. Next layer I want to use as a aluminum, and let's suppose another layer I want to use as a bottom incoherent layer. So I want to define air in the bottom sides. As an example, this is my layer structures. Layer stack in the right side you can visualize here, and I want to define this my thickness of aluminum electrode. Let's suppose as example 500 nanometer, and all things I want to keep it same. Now this is my layer. So first layer is glass where thickness is unimportant because it is treated as incoherent. This top layer and transparent. This is incoherent and transparent layers. Okay, you can see here, and we can define these other layer either incoherent, transparent, isotropic, emitter type, whatever type of layer we have to select from there. And then there is a cell comprises of ITO with a thickness of 125 nanometer, P dot with thickness of 50 nanometer, P3HT PCBM with thickness of 100 nanometer, and finally the aluminum with 500 nanometer thickness. And I would like to import the corresponding refractive index file for these material as it is listed. So this is air on the top. The refractive index is default defined 1 and 0. This is called refractive index of the material air on the top. So each material refractive index need to be defined. Now I will click on this glass layer where I will set the refractive index of this glass layer. So real part that is called n. I want to define n equal to 1.5 for this glass. For air I defined 1, and for glass layer I defined the real part 1.5, imaginary part 0 for all those layers. So in the solar cell, top and bottom layer representing the corresponding medium must be transparent. So top and bottom layer, this should be the transparent layers that we can define it. And these are incoherent layers. Top layer, bottom layer, top air and bottom air layer is called transparent and incoherent. And the convention for the direction of light in coupling in SETFOS, the light is always arriving from the top. So here you can see the light will always arrive on the top, but we can also make it reverse if you want to put it from the bottom. But defaultly it will take from the light is arriving or absorbing from the top. So in this case the light will be absorbed from the glass to the active layers, from the glass to the active layer. This is the reference direction for the calculation of reflectance and transmittance of the thin film structure. Now I would like to set this glass layer also become as a incoherent. I want to activate this layer as a incoherent. Now you can see this is also incoherent. If the layer thickness, if the thickness larger than 500 nanometer, the number of calculation points should be reduced. That should not be more than 100 point in this delta elements. So this is default 100 points. Now I want to set up the calculations. I want to run the job. So for that I want to define my name of project, that is called solar optical property. So I want to give the name solar minus optic. So I click on this run button to run the program for optical analysis. And for that I also need to enable the module. As in the presentation I told you, for optical analysis the module need to be enabled. So I click on this absorption and the optical absorption module has been updated. This is enabled. These are top module: absorption, drift diffusion, emission, and advanced optics scattering. So absorption module is enabled. Defaultly 300 780 to 780 wavelength is defined. But if you want to define some different wavelengths, you can define the wavelength as per your convenience. And this is a illumination spectrum. Defaultly 1.5 AM 1.5 is taken. I will click on this import button, and there is different sun spectrum is there. It is given in the library. Some AM0, AM 1.5, direct spectrum, and different other spectrum file is there for light, air mass 0 or different spectrum. Even if you have some intensity and wavelength parameter, the user can also give their own spectrum value. That is also possible. Now I want to run this project, solar optical. Now the simulation is running, and you can see here. Now I would like to click on this layer absorptance. Just a minute. So basically I have to define the optical property of each layer first. So glass layer, I defined this 1.5 real parts. And now ITO layer, P dot layer, P3HT, PCBM layer, aluminum layer, all these layer refractive index need to be defined. So what I will do, I will go to this ITO. Here I can define either my constant refractive index, or I can import the file from my directory. So I will click on this file option. Now here you can see there is a new refractive index. If you know the wavelength and NK value, then you have to define this refractive index. So I can create the new refractive index by clicking on this create new optical. Here there is a three option: NK file, EMA file, AD file. NK is called real and imaginary part of refractive index. EMA stand for effective medium approximation, and AD stand for analytical dispersion for Cauchy, Selmier, Drude, Lorentz, Tau models. Initially, let it take NK file refractive index. So if you know the property of refractive index, then you have to define here. You have to click on this add button. The first row is added. In this first row, I will add the wavelength value and real part, and this is imaginary parts. As an example, I am taking it. Then I will click on the next button to add it. This is, let's suppose, whatever the new value you have, that I can add it, and then I can add the new different other value. Similarly, the real part and imaginary part need to be added in this particular manner. In this particular procedures, just follow it and create the real and imaginary part of refractive index for this ITO layer. As an example, I am giving you, and whatever you have third party data, you can directly upload. That is also possible. And now you can see here, it is a graphical representation. If you want to check in the script, this is a script that is automatically generating from the graphical representations. So either you can type in the script, or you can give as an input in this graphical forms. These are bi-directional. If you want to copy paste here, then it is also possible. You can make a copy paste of your value, and you can also edit the value in this editor, and it will reflect automatically in this graphical. You can add or delete particular layer from there. So this is graphical and script, both are possible. Whatever you want to use according to your convenience, that can be used by you. And then you can click on save button. It will save the particular refractive index of the material. Once you click on this OK button. Now this is one procedure. If you want to import from the library, you can see there is an option called import. I click on this import button. I would like to import the material from my library. So this is my library of the material which is given inside the tool. So I will go there and I have to select the ITO. These are complete list of material refractive index with NK file dot NK extension is given that represent the real and imaginary part of refractive index. There is huge list of material are there. If any material are missing, the participants can also add your own parameters. It is also possible. Custom defined material. I would like to add ito.nk file. So I select it and click on open it. It is now added. You can see the real part and imaginary part. Black one is called real part and red one is called imaginary part of refractive index with respect to wavelengths. If you want to edit the existing value from the database, you want to edit it, then it is also possible. You can see here it is added automatically. I click on the edit button and it is, you can see how many wavelength value and what is n value and k value. First column is wavelength, second column is real part n value, and third column is called imaginary part k value. So real, imaginary and wavelength, three a column and three values are mentioned according to the graph is plotted. So this is wavelength dependent real and imaginary refractive index of this ITO materials. Next material we have that is called P dot. So I will click on this P dot material and go to this constant option and would like to import the material once again from my library. Either I can define my new material or I can import from the library. Click on import button and type P dot. So this is called P3HT PCBM layer. I need to import the material. So I will go to the P dot and check it. Where is the, these are certain P dot material are there. So I would like to take it this P dot bytron something and would like to import it. You can see this is imported. If you want to check this edit button, this is the value, wavelength, real and imaginary part. From the library I am importing it, and what is the reference? From this particular reference, the data of this P dot material is taken. P dot PSS, refractivity, resistivity. From this particular HC star website, the value is taken here. And next is called the P3HT PCBM. So I click on this P3HT PCBM and click on file option and click on import option and click on import button, where I will import the P3HT PCBM refractive index. So I click on this and you can see .nk file is there. Different other extension for different other material, electrical material, the EM extension is there. I click on OK and it is imported for P3HT PCBM refractive index. Next is called aluminium. So I click on aluminium and click on file option and click on import option and select the aluminium.nk file, and refractive index is loaded for aluminium.nk as well. So for each material refractive index nk file is loaded. Now I want to run the calculation, then we'll find the optical properties. So it is done. Now you can check the reflected color, and if you want to check the layer absorptance, like which layer you are getting more light absorb. So these are different layer. Glass layer, that is a top layer is called red one, that is called air layer, unipolar air layer. Then this blue layer, that is zero glass layer is there, that is called blue. And this ITO layer, this is called green layer, which is not showing because it is overlapping with some different layers. So this is red one is called glass layer. I want to hide it. So red layer has been removed. This is blue layer, glass layer, layer absorptance. This is ITO layer, which is you can see on the 0 layer absorbance. So I can also hide that layer. And this pink one is called the P dot layer, wavelength dependent absorbance. And the next one is called this P3HT PCBM and aluminum. This is the aluminum. This one layer, green one type, this is called aluminum. So which layer will get more light absorb? That display is showing here. So we can see the spectral range between 375 to 650 something. At this particular absorbance, P3HT PCBM layer is highly absorbing. This layer P3HT PCBM graph, which is highly absorbing layer, that will absorb the high light. If you want to click on this absorption profile, you can also see in this absorption profile P3HT PCBM highest light absorbing materials. Now you want to vary the thickness of this active layers. You can also see in the planar structure, this is plane, and this with their particular name of material: air, glass, ITO, P dot, P3HT PCBM, aluminum, and air bottom. And this is called planar structures. Now if you want to vary the thickness of your active layer, this P3HT PCBM as example your active layer. I am taking a common material for as per the all convenient participants, as around 150 participants have joining this demo. So accordingly I am taking one normal parameter, and whatever your particular material, your particular research, that can be taken care later. Now I want to activate the sweeping. I want to optimize the layer thickness. So I will click on the sweep button. This is now I want to vary the thickness of active layers. So what I will do, I will click on this sweep button. Once I will click on this sweep button, the sweep setting parameter is enabled. This parameter will be help you to define the minimum value and maximum value of particular material parameter. So now we will vary the thickness of active layer P3HTP and investigate the impact, the maximum generated ISC and different apparent color cells. So I will click on this. I have to select the layer and their parameter that I want to sweep from minimum value to maximum value. So optical parameter you can also sweep: wavelength, latitude, longitude, energy, and other. And also you can also sweep the thickness. So let's suppose P3HT PCBM layer thickness you want to sweep. You can also sweep the refractive index as well, real part, imaginary part. Not only single parameter, multiple parameter simultaneously you can sweep. You can sweep the thickness, voltage, wavelength, temperature, and refractive index, homolumo, density, doping, mobility, all as much as maximum. You can also simulate. So initially let it take P3HT PCBM to sweep it. So I selected it. Here there is a minimum range from value and maximum range. So let's say example 10 nanometer minimum and 200 nanometer maximum, and with a step size of 10. Step size in the sense increment of 10. So 10 nanometer, 20 nanometer, 30 nanometer, 40 nanometer, 50 nanometer, 60 nanometer, up to 200 nanometer. The software will do the calculation at each 10 steps. If I want to reduce to 5, then at each 5 steps, software will do the calculations. And the unit is in nanometers. So different unit can also be taken from here as well. Now I want to define this name of the project, sweep thickness, so that I can identify, and click on this run button. Now sweeping is done, as we have defined the thickness sweeping, so time is also increasing. But this software is very fast in algorithm. It will not take too much time. Within 2 minutes, 5 minutes, 10 minutes, the software will simulate your device structures. So it is done. Now I will click on the photocurrent, optical analysis photocurrent. So you can see here, this is the photocurrent with variation of active layer P3HT PCBM from 10 nanometer to 200 nanometer thickness. And which layer is having more photocurrent, that you can see here, at what thickness you are getting the maximum photocurrent value. So short circuit current as a function of P3HT PCBM thickness. This is the ISC value. Now you can see here, this red graph is called the glass layer. This blue one, which is not visible because it is hiding with this red one. And this green one layer, this is called this layer, which is called the P dot layer. And this pink one is called P3HT PCBM layer. And the ISC you can see from 10 nanometer to 25 nanometer variations. So this is all optical calculation of this simple layer stack that I have shown you. This is a layer structure, right side visualization. Spectrum we have taken it, AM 1.5. Different other spectrum is also possible. Some single byte spectrum or even location specific, time specific. If you want to check the realistic condition, the light absorbed in your device, but based on theoretical analysis, realistic condition in the sense some daytime may have different spectrum, evening time may have different spectrum, morning time may have different spectrum, or in different time zone or different location, you can also study the realistic condition spectrum. That's why this latitude, longitude, elevation, date, time, you can see the calendar is also given. So based on presumptions, it will calculate the realistic, it will try to calculate the realistic spectrum and light absorb. As you know, the Delhi may have different spectrum, in Guwahati may have different spectrum, in Mumbai may have different spectrum. So that's why this is a location based spectrum condition which will not be available in any of the softwares. Now this is all about optical calculations. If you want to go for the electrical calculations, for IV calculations, for optical electrical behavior of bulk heterojunction solar cells, then I have to enable the drift diffusion module, that is for electrical analysis. So you can see this is a drift diffusion module. I click on it. Now once I click on it, the drift diffusion absorption module is enabled. Now you can see this is a drift diffusion settings. When I click it, it will enable it. Now I want to convert this optical solar cell study into the electrical one to perform the optoelectrical calculations. Now I want to set my layer, which layer as a semiconducting and which layer as a electrode type. So I click on this P3HT PCBM layer and I want to set as a semiconducting type. So this is a semiconducting. Once I click on it, this tab is enabled. If I deselect it, the semiconducting tab will be disabled. So parameter will be enabled based on the selected feature. So I click on it, it will select it, it will enable and disable based on the particular selected parameters. You can see here. Now I have to import the semiconducting material property as well. Previously I imported the NK refractive index. NK refractive index is called optical property. But for semiconducting property, either I can define my own property. For that I have to click here and define the property, or I will click on this import button Once I click on this import button, just a minute, there is an option called semiconducting property. Here I can click on this import button. Either I can write the script or export it. So I click on this import button for semiconducting property of the P3HT PCBL layer, and you can see this is a library which is already given in my database, and these are materials, semiconducting material. .em is the extension for these all material that you can find it. So P3HT PCBM, I can import this layer electrical material. .em extension is there, that is called electrical material, semiconducting material. I imported. For the time being, I want to hide the layer structure and energy level by clicking on this display layer stack, so that I can visualize my structure properly. Later on, if I want to visualize, I can click there and it will enable it. So hiding and enabling and disabling can be done by double click on this particular right top particular features. Now you can see on the bottom of the page there is charge transport layers. Homo Lumo is there. Homo value, Lumo value, that is default taken from the library when I imported the materials. Default dielectric constant value is mentioned. This is called acceptor doping, donor doping. If you want to dope particular layer, then this feature need to be enabled and define the concentrations. 5 e to the power 15, 16, whatever. You can define the concentration of the particular layers. I want to hide it initially. Whatever the parameter imported from the material, I want to use that parameter. Now, next one is called mobility, electron mobility and hole mobility. So this is electron mobility is given 0.001 centimeter square per volt second, and this is 1 e to the power minus 6 centimeter square per volt seconds. So constant mobility in open source may be only constant, but this license tool have constant, field dependent, field temperature dependent, EGDM, ECDM, extended Gaussian type disordered, correlated type disordered, field dependent type. These are different state of art mobility model that will help you to enhance your efficiency of the device. That's why commercial tool play a major important role. Now if you go to the excitons, new tab exciton, I can click on this add button and the multiple excitons can be enabled. Exciton are usually required for LED, TADF, thermally energy transfers, radiative, non-radiative, diffusion constant, saturation, annihilation, triplet, singlet, interaction, quenching, polar energy transfer rate. For that purpose, these excitons need to be enabled. I want to hide for the time being. In second section, we will try. And this is a trap. If you want to capture the electron hole, you have to enable this traps. Bulk traps are there. Click on this traps, enable trapping. SRX recombination for the traps. Trap recombination. Once you enable these features, it will get it enabled. So multiple traps options are there. Single energy level traps, exponential density of state traps, Gaussian density of state traps. These are all traps parameters. Electron hole capture rates, traps. So the trap need to be specified, the recombination parameters. And next one is called mobile ions, anion and cations. If you want to define, this is anion and cations. Once you enable the checkbox, this is anion and cations. So you can associate that particular mobility model with that particular type of anions. Static type, constant type, field dependent type, temperature dependent type. As you know, in field of research, there are so many factors are there, so many parameters are there. Once you will try to do different kind of new parameter enabling accurate parameters, then you will find the good efficiency. Now next is called the recombinations. So you can also use the Languin recombination, Auger recombination, bimolecular recombination, and simplified recombination parameters. And bottom of the page, if you want to do the reverse breakdown, impact ionization model are there. You can enable the impact ionization. And in the impact ionization, China with linear and Thornburg models are there. And you can select the particular impact ionization prefactors value you can set in this particular options. Similarly, China with linear models are there and Thorburner models are there. With electrical electron optical phonon threshold field and whole optical phonon threshold field. These are all parameters for the impact ionization. That research can be done by you by enabling the particular options. So this is all semiconducting parameter for each material. I have initially taken the P3HT PCBM imported from the library. If you would like to visualize the script, click on this script button, and this script will help you to check the automatically imported code from our library. Whatever the model, whatever the parameter, whatever the input of this semiconducting layer are there, that is given in the form is this script. So you can see the HUMO-LUMO is mentioned, epsilon, dielectric constant are mentioned, density of state, optical efficiency, electron and hole mobility, field dependent mobility. These are all parameters are mentioned. Now I want to close it. I want to close it. And you can see here this P3HT PCBM layer. We have enabled the semiconducting parameters. Now I want to follow the electrode. So I will click on this layer as an example. I can also use this P3HT PCBM layer as a semiconducting. I can also use it, but initially I want to define as an electrode and with their work functions. And bottom aluminum electrode, I can also take an ITO as electrode and would like to define the work functions. Ohmic type work function is given there 4.5, but I want to use only 4 electron volt work function for this P3HT PCBM layer. Similarly, for this layer, I want to use different work functions. So this is 4.0 and P3HT PCBM 4.8 something. I want to take it, and both are ohmic type boundary condition. Thermonic is also possible. Thermonic work function and ohmic type. Now once it is done, then I will go to the to calculate the current voltage characteristics. I will go to diffusion setting, and steady states calculation is possible. Transient simulation is possible. AC impedance, and IMPS, IMBS, intensity modulated photovoltage and photo current spectroscopy analysis. So let it perform the steady states calculation, and here it is voltage sweeping. So drift diffusion and absorption, both model are active and both are coupled to each other defaultly. So to activate the optical generation of charge carrier in P3HT PCBM layer, the optical generation efficiency that we can set zero to 1, and I will go to the sweep setting. So in this sweep setting, I want to sweep the voltage. So, so I will click on this three dot and click on this electrical and select the voltage option. Just a minute. Earlier I already selected the thickness. So first of all, active layer thickness, and next I click on this plus button, and next I want to sweep the voltage. So two parallel parameter I want to sweep it, and here I can define the minimum 1 volt to maximum 1 volt I want to set. And with an increment of 0.1 step size. Now I want to define the name of this project IB and click on run button. So simulation is going on as you can see on the screen. So once the parameter are increasing, the time may be increasing accordingly. Now you can see this is a photocurrent with respect to thickness variations, and voltage is constant at minus 1 volt. If I will sweep the voltage, there is no change on the photocurrent of the voltage parameters. Now I want to click on this device current. This is device current. I can zoom it. Now you can see from thickness variations. If you want to vary the thickness, then how the graph will be changing from minus 1 volt to plus 1 volt. So you can see not only a thickness variation, voltage and current, whenever we will increase the voltage from negative to positive, then how the device current will be changed. Similarly, all characteristics are there. This is power conversion efficiency from negative biasing to positive biasing. Right side you can see here. Now similarly, if you want to plot other characteristics, this is a band diagram. I want to zoom particular regions. This is band diagram in between the electrode. With thickness variation, how the band gap will be changes, and if there is a voltage effect, this is a voltage variations. So two parameter can be swept at a time: voltage variation and thickness variations. And other plot you can see it, charge density. Maximize these regions, and you can see the charge analysis in between the electrode. So charge density, electric field, recombinations, how much the recombinations are taking place in graphical form, as well as language recombination and different other parameters. If you want to do the absorptance, this is a total device absorption with thickness 10, 20, 30, 70, 80, 90. How the P3HT PCBM active layer thickness sweeping, absorptance graph are changing. Similarly, if voltage variation are there, then it will also show you. This is absorptance without any polarization. This is S polarization and P polarization. And this is total device absorption, particular layer wise, which layer will get more light absorptance with thickness variation and voltage variation. If there are any voltage variations are there, this is transmittance. So transmittance, reflectance, conductance, all things can be done. So this is simple structure that I have taken and tried to show you. Now if you want to add some more complicated parameter, you can also add it. Let's suppose now we want to change the structure. We want to take it, I want to deselect as electrode. I can add more layer on the bottom side. I can click on this add layers. Let's suppose this is my ETL layer. So I can add electron transport layer, perovskite layer, HTL layer, and I can define this ITO as electrode type. This is as a semiconducting type, and this HTL also as a semiconducting type. If that kind of structure you want to simulate, you can see in this right side. I have to define the semiconducting parameter for these layers. Or it will be a whole transport layer, and this will be a whatever you want to define the convenient. And there I have to define the semiconducting parameter. So go there and click on import button. So if you want to take P3HT PCBM as a semiconducting, you have to import the semiconducting parameter as well as refractive index. Next is called this perovskite layer, where I have to define the perovskite layer semiconducting property. So ion transport I imported, and refractive index I also need to. So refractive index, optical property as well as electrical semiconducting property EM file. So this is NK refractive index for CH3, NH3, PBL3 and different other perovskite layer. I can take whatever the convenient material I want to take and click on open. This is ETL, and I can click on that. If you want to take Spyro as example, Spyro omitted, I import it, and refractive index of that particular same material will be associated. Spyro omitted and imported. Now if you want to run it, just simply click on this run button. Now simulation is going on, as you can see on the screen. Wait for 2 minutes. Now simulation is done. You can see the transmittance curve is plotted with wavelengths dependent. You can see the wavelengths. I am taken the random structures. So perovskite layer thickness is changing, and this is voltage dependent variations. If you want to see the device current, this is a device current variation of the voltage. And if you want to see the thickness variation, this is thickness variations characteristics. If you want to export the data, you can simply right click and click this visible data. Save this visible data. You can save in the form of text, in the form of Excel, whatever the format. You can save the data and click on desktop. It will save it. Similarly, power density characteristics in the graphical form as well as in the representations. This is power conversion efficiency, power density. Multiple graphs can be plotted and see the characteristics. And this is graphical power conversion efficiency. Electrical band diagram, thickness variation, and voltage variation. At what voltage, based on theoretical model, the output will change. That study you can perform. Similarly, charge density and all the plot. Charge density, charge generations, current, electrical field, potential, recombinations. Photocurrent, it's a photocurrent, thickness variation or voltage variation. You can see like that. Now if you want to add the interface in between HDL layer and perovskite layer, simply click on this add interface layer. So single interface can also be added. You can enable this exciton dissociation, diffusion length top, diffusion length bottom, generation efficiency for bottom. Hopping interface are there. You can define the hopping interface for basics and other, and you can enable the traps for this particular interface, SRH trap for this particular two different layer interface, enable trapping, SRH trapping, recombination trapping, and define their parameter. Similarly, interface recombination. This is interface SRH recombination with their electron recombination velocity, hole recombination velocity, and trap energy offset. Similarly, this is another one where you can also add the interface by simply click on this layer. So n number of layers you can define and you can create your structures. You can see there are two interfaces are there which is visualizing in the layer structures. So the parameter need to be defined for that particular enabled interface. Whatever the parameter, whatever the value that you know, that need to be defined. If you have no value, you can delete this parameter, and this is like that. Now if I want to show you the more complicated structures, some tandem based structure as well, so I would like to open one tandem solar cells. In this left side you can see this is a example default library. Basically it is a license version tool which need to be purchased by your institute. It is not a free software. You can see these are a couple of examples are given for even for OLED, different kind of OLED structure and different kind of solar cell as well. Example given in the directory. So these are few full solar cell. This example I imported solar cell bi-layer with ID MO03 CY3 interface C60 ALQ. This material is used. Let us simulate this particular example. It is simulating fast and you can click on this device current. This is device current plot. One is called JB curve. This is called JB curve, red one with rank with the recombinations parameter and with Langevin recombination. So SRH Langevin recombination both are same. That's why this JB curve are showing. Without recombination, with the recombination, the device current from -1 volt to +1 volt. Similarly, the power conversion efficiency, power density analysis, and this is a display key figures. If you want to see the BOC value, GSC value, you want to see the fill factor value, maximum power density, maximum power conversion efficiency. So the efficiency of the parameter need to be increased. Now if you go in the next one, this is called Venn diagram from minus to plus like that, and with HUMO-LUMO as well, and absorptance, layer specific absorptance, reflectance, transmittance for this particular structures. If you want to see other structure, this is another structures. If you would like to see the perovskite, other complicated structure, this you can see in this particular example. ITO, PTTA, this different organic material, interface, perovskite, CSFA, PBL, BR3, C60, BCP, and CU and airbag. This is structure. Right side you can visualize and let it simulate this perovskite hysteresis and click on run button. So it is simulating. So it will take 2 to 4 minutes. In the meantime, simulation is going on. In the meantime, I would like to show you other example which is given in the directory. You can see this is another example, perovskite IV, perovskite transient. So this perovskite hysteresis